An electron can remain inside an atom for billions of years. It can belong to matter that existed long before Earth formed, survive through the birth and death of stars, become incorporated into new atoms and molecules, and continue behaving exactly like every other electron in the universe. It does not become tired. It does not gradually lose its electric charge. And most strangely of all, when an electron occupies a stable state inside an atom, it does not seem to slowly run out of the energy associated with that state. At first, this feels impossible. Almost everything familiar to us requires energy to keep going. A car eventually runs out of fuel. A battery becomes empty. A spinning wheel slows because of friction. A living organism needs a continuous supply of chemical energy simply to remain alive. So if an electron is somehow moving around an atomic nucleus for an enormous amount of time, what keeps it going? Where does the energy come from? And why has the atom not eventually gone dark and collapsed? The problem becomes even stranger when we use the picture of the atom that many of us first learned in school. At the center sits a tiny positively charged nucleus. Around it, negatively charged electrons appear to orbit like planets around the sun. It is a simple and memorable image. It is also fundamentally misleading. If electrons really behaved like tiny charged planets following classical orbits, stable atoms should not exist. According to classical electromagnetism, an accelerating electric charge emits electromagnetic radiation, and an object traveling in a circular orbit is continuously accelerating, even if its speed remains constant, because the direction of its velocity is constantly changing. A classical electron orbiting the nucleus should therefore radiate energy into space. As it loses energy, its orbit should shrink. As the orbit becomes smaller, the electron should spiral inward faster and faster until eventually it crashes into the nucleus. The entire process should happen extremely quickly. Matter as we know it should collapse almost immediately. Clearly, that is not what happens. The atoms in your body have not collapsed. The atoms in the air have not collapsed. The atoms making up Earth have survived for billions of years, and atoms throughout the observable universe appear to obey the same fundamental rules. So by the beginning of the 20th century, physicists faced a serious problem. Classical physics had become extraordinarily successful at describing planets, projectiles, machines, electricity, magnetism, and light. Yet when those same ideas were applied to the atom, they predicted a universe that could not remain stable. Something about the picture had to be wrong. One of the first major steps away from the classical atom came from Niels Bohr in 1913. Bohr proposed that electrons could occupy only certain allowed orbits around the nucleus. Instead of being able to possess any arbitrary energy, the electron could exist only at particular, discrete energies. It could transition between them by absorbing or emitting specific amounts of energy. This was revolutionary because it introduced the idea that atomic energy might be quantized. Imagine a staircase rather than a smooth ramp. On a ramp, you can stand at any height. On a staircase, only particular levels are available. Bohr suggested that something similar happens inside the atom. The electron cannot simply slide continuously downward through every imaginable energy. It occupies allowed states. When it transitions from a higher energy state to a lower one, the difference in energy can be released as a photon. When it absorbs the correct amount of energy, it can move upward. This helped explain why atoms produce specific spectral lines. When hydrogen gas emits light, it does not radiate every possible wavelength equally. Instead, it produces a characteristic pattern of discrete wavelengths. These correspond to specific differences between allowed atomic energies. Bohr's model captured something essential. Atomic energy really is quantized, but the idea of electrons following literal circular orbits still had to disappear. The deeper revolution came with quantum mechanics. In quantum mechanics, an electron inside an atom is not described as a tiny object following a precise path around the nucleus. Instead, it is described by a quantum state, represented mathematically by a wave function. That wave function allows us to calculate probabilities for the outcomes of measurements. If you measure the position of an electron, you can detect it at a particular location. But before that measurement, Quantum mechanics generally does not describe it as a tiny ball traveling along one hidden classical orbit that we simply cannot see. The familiar pictures of electron clouds around atomic nuclei come from this quantum description. An orbital is not an orbit. That difference is crucial. An orbit is a path. An orbital is a quantum state. For hydrogen, the simplest atom, the lowest energy electron state is distributed around the proton in a spherically symmetric way. There is no little electron circling clockwise or counterclockwise. There is no miniature planetary track. And once the classical orbit disappears, the classical radiation problem disappears with it. The electron in a stationary atomic state is not a charged particle undergoing the kind of classical orbital acceleration that would continuously radiate energy away. The quantum state can have a definite energy and remain stable in time. This is the first major answer to our mystery. The electron does not need a continuous supply of energy to maintain an orbit because there is no classical orbit to maintain. But this immediately creates another question. If the electron is attracted to the positively charged nucleus, why does it not simply collapse into it anyway? Opposite electric charges attract. Bringing the electron closer to the proton lowers the electrostatic potential energy. So why shouldn't the lowest energy state place the electron directly inside the nucleus? This is where quantum mechanics becomes even stranger. The electron cannot simultaneously have an arbitrarily precise position and an arbitrarily precise momentum. This is the Heisenberg uncertainty principle. And despite the way it is sometimes described, this is not merely a statement about bad measuring equipment. It is not that the electron secretly possesses a perfectly definite position and momentum, and we are simply too clumsy to determine both. The uncertainty is built into the quantum state itself. If we try to confine an electron to a smaller and smaller region of space, the spread in its possible momentum becomes larger. And because momentum contributes to kinetic energy, extreme confinement becomes energetically expensive. So inside hydrogen, two effects compete. The electrical attraction between the electron and proton favors bringing them closer together. Quantum confinement resists squeezing the electron's state into an arbitrarily tiny region, because doing so increases the kinetic energy contribution. The result is a lowest energy configuration with a finite characteristic size. The electron does not need an invisible force holding it away from the nucleus. There is no microscopic shelf. There is no tiny barrier surrounding the proton. The stable size of the atom emerges from quantum mechanics itself. And this lowest energy configuration is called the ground state. The ground state is one of the most important ideas for understanding why electrons never seem to run out of energy. An atom can be excited. Perhaps it absorbs a photon. Perhaps it collides with another particle. Energy enters the system, and the electron occupies a higher energy state. That excited state may not remain forever. The atom can transition downward and release energy. Eventually, however, it reaches the ground state, and then the downward staircase ends. There is no lower ordinary bound electronic state available. The electron cannot continue releasing smaller and smaller amounts of energy forever while remaining bound to the atom. It has reached the bottom. This is where our everyday understanding of energy often causes confusion. When we hear that an electron has energy, we instinctively imagine energy as fuel. If a car has fuel and keeps driving, eventually the tank empties. If your phone has battery energy and remains active, eventually it needs charging. So if an electron possesses energy, shouldn't it eventually use that energy up? No. Having energy is not the same as consuming energy. Imagine a stone resting on a shelf. Relative to the floor, it has gravitational potential energy, but the stone does not spend a tiny amount of that energy every second merely by remaining on the shelf. Or imagine an object moving through perfectly empty space with no forces acting on it. Newton's first law tells us it can continue at constant velocity indefinitely. It does not need an engine continuously providing energy simply to maintain that motion. Cars require fuel to maintain speed because they experience resistance. Air drag, friction, deformation, and internal losses transfer energy away. Remove those losses, and constant motion itself does not require constant power. The same conceptual distinction applies to quantum states. A stationary atomic state can possess energy without consuming it. If there is no process transferring that energy somewhere else, there is nothing that needs to be replenished. And in the ground state, there is no lower electronic state available into which the atom can simply radiate. The electron has not run out of energy. The system has reached its minimum allowed energy. Those statements sound similar, but physically they mean completely different things. An empty battery has lost usable stored energy to its surroundings. A ground state atom still possesses energy and structure. It is simply already in the lowest energy electronic configuration allowed by the quantum system. For hydrogen, physicists often define the energy of a completely separated electron and proton as zero. With that convention, the ground state energy is approximately minus 13.6 electron volts. The negative sign tells us that the electron is bound. Energy must actually be supplied if we want to separate it completely from the proton. So even the lowest atomic state is not a state in which the electron somehow possesses nothing. It is a stable bound configuration, and the electron inside it still has a kinetic energy contribution. That may sound contradictory. If the electron is not orbiting, how can it have kinetic energy? Again, the problem comes from forcing quantum mechanics into classical language. Quantum kinetic energy does not require a hidden circular trajectory. It is connected to the momentum content and spatial structure of the electron's wave function. A confined quantum state naturally contains a spread of possible momentum measurements. The average momentum can even be zero, while the kinetic energy remains positive, because kinetic energy depends on the square of momentum. Equal possibilities for momentum in opposite directions can cancel in the average momentum while still contributing positively to energy. The electron, therefore, does not need to be secretly racing around the nucleus to possess kinetic energy. The energy belongs to the quantum state. And now the original mystery begins to reverse itself. At first, we wondered what could possibly keep the electron going forever. But that question assumed there was something that needed to be kept going. A classical orbit, a continuous expenditure, a tiny machine that should eventually stop. Quantum mechanics tells us that none of those things exist inside the atom in the way we imagined. The electron occupies a stable quantum state. The ground state does not continuously radiate. Its energy is not being spent merely because time passes, and there is no lower electronic state into which it can endlessly collapse. But this is only the beginning of the answer. Because if an electron is not following a path around the nucleus, then what exactly is it doing? Is the electron really spread throughout the entire orbital? Is it secretly somewhere inside the probability cloud? Does it move when nobody measures it? And how can something possess momentum and kinetic energy without following a definite trajectory? To understand why the electron can remain stable for essentially unlimited periods, we need to leave the image of the tiny particle behind even further. We need to ask what an electron inside an atom actually is. The image of an electron circling an atomic nucleus is difficult to let go of because it feels so natural. A positively charged nucleus sits at the center. A negatively charged electron is attracted toward it. If the electron does not fall inward, then surely it must be moving sideways quickly enough to keep missing the nucleus, just as Earth continuously falls toward the sun, while its sideways motion keeps it in orbit. This picture seems to explain both the attraction and the stability at once. But at the atomic scale, nature does not work this way. There is no tiny planetary system hidden inside ordinary matter. The electron is not tracing a circular path around the nucleus, and once we understand what replaces that path, the question of where its endless energy comes from begins to disappear. In classical mechanics, describing an object usually means describing where it is and how it is moving. If you know the position and velocity of a planet, you can calculate its future trajectory. The same idea works for a thrown ball, a spacecraft, or almost any ordinary object. At every moment, the object occupies some position, and from one moment to the next, it follows a continuous path through space. Quantum mechanics replaces this description with something fundamentally different. An electron inside an atom is described by a quantum state. That state is represented mathematically by a wave function. The wave function does not simply tell us where a tiny hidden electron is located. Instead, it contains information that allows us to calculate probabilities for the outcomes of measurements. If we measure the position of the electron, we can detect it at a particular location. But if we prepare many identical atoms in the same state and repeatedly measure their electrons, we will not always find them in exactly the same place. The detections build a distribution. This distribution is what the familiar electron cloud represents. For the ground state of hydrogen, the probability distribution is centered around the proton and extends outward through space. There is a greater probability of detecting the electron in some regions than in others, but there is no narrow circular track around the nucleus. The electron cloud is not a blurry photograph of an orbit. That distinction is extremely important. Imagine photographing a racing car at night using a very long exposure. The headlights might form a bright streak along the road. Looking only at the photograph, the car seems spread across the entire path. But we know what actually happened. At each instant, the car occupied one particular location. The streak appeared only because the camera combined many moments into one image. It is tempting to imagine an atomic orbital in the same way. Perhaps the electron really is a tiny particle, moving incredibly quickly, and the probability cloud simply represents all the places it might pass through. Quantum experiments tell us that this classical explanation is not enough. One of the clearest demonstrations comes from the double-slit experiment. Send electrons toward a barrier containing two narrow openings, with a detector behind it. If electrons were simply tiny classical balls, each electron should pass through one slit or the other. After many electrons, we would expect a distribution corresponding to particles traveling through two separate openings. Instead, under the right conditions, an interference pattern appears. There are regions where many electrons arrive and regions where very few arrive. The pattern resembles what happens when waves pass through two openings and overlap. Even more strangely, the electrons can be sent through the apparatus one at a time. One electron is emitted. One localized detection appears. Then another electron. Another localized detection. At first, the detector seems to be collecting individual points almost randomly. But as thousands of electrons arrive, the interference pattern gradually becomes visible. Each electron is detected like a particle. Yet, the distribution of many detections reveals wave-like interference. This is not what we would expect if every electron simply followed one ordinary unknown trajectory. The quantum state evolves in a way that allows different possibilities to interfere. And when the experiment is modified so that information about which slit the electron passed through becomes physically available, the interference can disappear. The electron does not fit comfortably into either classical category. It is not simply a particle. It is not simply a wave. It is a quantum object. And the same quantum behavior exists inside the atom. An atomic orbital is a quantum state with a particular spatial structure and energy. Different orbitals have different shapes and properties. Some are spherically symmetric. Others have more complicated patterns with regions where the probability of detecting the electron becomes very small or zero. These structures are not arbitrary drawings invented to make chemistry easier. They emerge from solving the equations of quantum mechanics for electrons bound to nuclei, and their shapes help determine how atoms interact. This is where the strange behavior of a single electron begins to build the ordinary world. The arrangement of electrons around atomic nuclei determines much of chemistry. It influences which atoms bond, how molecules form, how materials conduct electricity, and why different elements possess different chemical properties. The solid objects around you ultimately depend on these quantum states. But before reaching that larger world, there is another mystery inside the orbital itself. If the electron is not following an orbit, why does it have momentum? And how can it possess kinetic energy? In classical physics, kinetic energy belongs to motion. If a ball is stationary, its kinetic energy is zero. Make it move faster, and its kinetic energy increases. So if the electron is not racing around the nucleus, it might seem that its kinetic energy should vanish. Quantum mechanics again refuses the classical picture. A bound electron can have zero average momentum, while still possessing non-zero kinetic energy. Suppose, only as an analogy, that a quantum state contains equal possibilities for measuring momentum in opposite directions. The positive and negative momentum values can cancel when we calculate the average. The average momentum can therefore be zero, but kinetic energy depends on the square of momentum. Squaring removes the distinction between opposite directions. Both possibilities contribute positive kinetic energy. So zero average momentum does not mean zero kinetic energy. More deeply, the spatial shape of the wave function itself is connected to momentum. A quantum state localized within a finite region cannot contain only one perfectly precise momentum. This is another expression of the uncertainty principle. Confinement in position requires a spread in momentum. That momentum spread contributes kinetic energy. This is why the electron in the hydrogen ground state can possess kinetic energy without following a classical path. Nothing needs to be secretly orbiting. The kinetic energy belongs to the structure of the quantum state. And once we understand this, the stability of the atom becomes much less mysterious. The electron is electrically attracted toward the nucleus. That attraction contributes negative potential energy to the bound system. If the electron's state becomes more concentrated near the nucleus, the potential energy contribution can become lower. But concentrating the state too strongly increases the momentum uncertainty and therefore raises the kinetic energy contribution. The ground state appears where these competing contributions produce the minimum total energy. The atom settles into a stable quantum configuration. There is no tiny electron constantly trying to escape. There is no fuel being burned to maintain a circular orbit. There is simply a quantum state with a particular energy. And if that state is stationary, its observable probability distribution can remain unchanged in time. This is another place where the word stationary can be confusing. A stationary quantum state does not mean the electron is a tiny object frozen at one position. It means the quantum state has a definite energy and its observable probability. Distribution does not change with time in the ordinary way an evolving wave packet might. The wave function itself acquires a time-dependent phase, but the probability density remains the same. The cloud does not gradually shrink toward the nucleus. It does not slowly lose energy. It does not become weaker because the atom has existed for too long. This is precisely what the classical model could not explain. In the old planetary picture, the electron continuously accelerates around the nucleus and should radiate electromagnetic energy. In the quantum picture, there is no classical orbit producing that continuous radiation. An atom can remain in a stationary ground state without emitting energy, and therefore there is no continuous energy loss requiring some mysterious source to replace it. This is the central misconception behind the question of why electrons never run out of energy. We imagine an electron performing an activity, orbiting, moving, working. And because activity in our everyday world often consumes energy, we assume the electron must eventually stop. But fundamental physics does not say that energy is consumed simply because something persists. Energy is conserved and transferred through interactions. A free electron moving through empty space does not slowly lose kinetic energy merely because it has traveled a long distance. If nothing interacts with it, its motion does not require fuel. Likewise, an electron bound in a stationary atomic state does not continuously spend its energy merely by remaining in that state. It can stay there indefinitely unless something interacts with the atom, and atoms are constantly capable of interacting. A photon with the appropriate energy can be absorbed, moving the atom into an excited state. A collision can transfer energy. Strong electromagnetic fields can alter the state. An electron can even receive enough energy to leave the atom entirely, a process called ionization. The stability of the ground state does not mean the atom is completely isolated from change. It means that if nothing supplies or removes energy through an allowed interaction, the ground state has no reason to decay further. And if an atom is excited, something interesting happens. The electron does not slowly spiral downward through continuously shrinking orbits. Instead, the quantum system can transition between allowed states. The difference in energy can appear as a photon. Suppose an electron occupies a higher energy state. If an allowed transition to a lower energy state occurs, electromagnetic radiation can be emitted with an energy corresponding to the difference between those states. This is why atoms produce characteristic spectra. Different elements possess different electronic structures, and therefore different possible energy transitions. When we examine the light emitted or absorbed by atoms, we see specific spectral lines. Those lines act almost like fingerprints. Astronomers can examine light from distant stars and determine which elements are present because atoms, billions of kilometers away, obey the same quantum rules as atoms in laboratories on Earth. The strange stability of the electron, therefore, gives us a way to read the chemical composition of the cosmos. And those spectral lines also reveal something important about energy. The electron does not possess a continuously draining reservoir. Energy enters and leaves through specific physical interactions. An atom absorbs energy and becomes excited. Later, it can release energy and transition downward. Eventually, it can reach the ground state. Then the process stops. Not because the electron has used up its final bit of energy, because there is no lower ordinary electronic state available. Imagine standing on the lowest step of a staircase. You can climb upward if energy is supplied. You can descend if you are already higher. But once you reach the floor, asking why you do not continue stepping downward misunderstands the structure. There is no next step. The atomic ground state is similar, although the underlying physics is far more sophisticated than the analogy. The energy spectrum has a minimum. That minimum gives the atom stability. And this idea of a minimum energy will become increasingly important as we move deeper into quantum physics. Because ground states are not unique to atoms. Molecules have them. Quantum oscillators have them. Fields have them. Even what we call empty space possesses a quantum ground state. Stability appears throughout physics, because systems cannot simply release energy forever if their allowed energies are bounded below. But before reaching the quantum vacuum, we need to understand something else. The electron cloud around the nucleus is not merely an unusual replacement for an orbit. Its structure determines why different atoms behave differently. Add more electrons, and a new quantum rule becomes essential. Electrons cannot all collapse into exactly the same state. They begin filling different available states, creating shells and orbitals, and eventually the repeating structure of the periodic table. And from that rule emerges almost all of chemistry. The reason carbon can build extraordinary molecules, the reason oxygen reacts as it does, and even part of the reason the matter around you feels solid can be traced back to the strange quantum behavior of electrons. So the next step in understanding why electrons remain stable is to move beyond a single hydrogen atom and ask what happens when nature begins adding more of them. Once we move beyond hydrogen, the atom becomes much more complicated. Hydrogen contains only one electron, making it the simplest place to learn the basic rules. But most atoms contain many electrons, all attracted toward the positively charged nucleus. And this creates another question. If lower energy generally means greater stability, why don't all the electrons simply occupy the same lowest energy state? Why should an atom need shells, orbitals, or any complicated structure at all? The answer comes from one of the most important rules in quantum physics, the Pauli exclusion principle. Electrons belong to a family of quantum particles called fermions, and identical fermions cannot occupy exactly the same quantum state within the same quantum system. For electrons in atoms, this means that once a particular state is occupied in the allowed way, additional electrons must occupy other available states. They cannot all simply pile into the same lowest state. This rule may sound like an obscure detail of particle physics, but its consequences are everywhere. It helps create the structure of the periodic table. It helps determine chemistry. It contributes to the stability and structure of ordinary matter. And it gives us another reason why electrons cannot simply collapse into one tiny region around an atomic nucleus. Imagine building atoms one electron at a time. Hydrogen begins with one electron. Helium has two. Those first two electrons can occupy the lowest spatial orbital because electrons possess another quantum property called spin. allowing two electrons with opposite spin states to share that orbital. Then we add a third electron to create lithium. That electron cannot simply join the first two in exactly the same set of quantum numbers. It must occupy a higher available state. As more electrons are added, they progressively fill different orbitals and shells according to the rules of quantum mechanics. This produces structure, and eventually, that structure produces chemistry. The electrons closest to the nucleus are generally bound most tightly. Electrons farther outward, particularly those in the outermost occupied states, play a major role in chemical bonding. Atoms interact largely through these outer electrons. Some atoms tend to lose electrons. Some tend to gain them. Others share electrons with neighboring atoms, creating covalent bonds. From those interactions come molecules: water, carbon dioxide, proteins, DNA, minerals, the atmosphere, your body. Almost all of ordinary chemistry emerges from how electrons arrange themselves according to quantum rules. This is a remarkable thing to consider. The periodic table looks like a catalog of different substances. Hydrogen behaves differently from carbon. Carbon behaves differently from oxygen. Oxygen behaves differently from iron. Yet underneath those differences, every electron is fundamentally the same kind of particle. An electron in carbon has the same rest mass and electric charge as an electron in hydrogen. An electron inside your body has the same intrinsic properties as one inside a star on the opposite side of the galaxy. What changes is the quantum environment. Different nuclei contain different numbers of protons, producing different electric fields. Different numbers of electrons then occupy different, allowed quantum states around those nuclei. From identical electrons arranged according to the same fundamental rules comes the enormous diversity of chemistry. And none of those electrons needs to continuously consume energy merely to remain in its allowed state. This brings us back to the central question. When an atom is in a stable electronic configuration, the electrons are not constantly spending energy to preserve that arrangement. The configuration itself is a quantum state of the system. Energy would need to be transferred if we wanted to change it. For example, shine light of an appropriate frequency onto an atom, and it may absorb a photon. The atom gains energy and enters an excited state. But not every photon will work. If the energy does not correspond to an allowed transition, the interaction may not produce the transition we want. This is another consequence of quantization. The atom does not behave like a bucket into which we can pour arbitrary, tiny amounts of energy until the electron slowly rises outward. Its electronic states have structure. When an allowed transition occurs, the system changes from one quantum state to another. And when an excited atom returns to a lower energy state, it can emit a photon carrying away the energy difference. This happens constantly throughout the universe. It happens in laboratory gases. It happens in flames. It happens in the atmospheres of stars. It happens in glowing nebulae across interstellar space. And because the allowed energy differences depend on the atom, the emitted photons form characteristic patterns of wavelengths. That is why astronomers can determine what distant stars are made of without ever touching them. Light travels across space, carrying the signature of quantum transitions that occurred inside atoms. The stability of electronic states is therefore not merely an abstract feature of microscopic physics. It is something we can observe written across the spectrum of the universe. But there is another consequence of electron structure that is even closer to everyday experience. Right now, you may be sitting on a chair or lying on a bed. Your body does not pass straight through it. That seems completely obvious. Solid objects are solid. But at the atomic scale, solidity becomes surprisingly mysterious. Atoms are mostly what we casually call empty space. Their nuclei are extraordinarily small compared with the overall size of their electron distributions. If we imagine matter as tiny hard balls packed tightly together, we are already using the wrong picture. When your hand presses against a table, the nuclei in your hand are not simply colliding directly with the nuclei in the table like billiard balls. The electromagnetic interaction between the electronic structures matters enormously, and the Pauli exclusion principle also becomes important when electron states begin to overlap. Electrons cannot simply all collapse into identical occupied states. As matter is compressed and electronic wave functions overlap, quantum mechanics strongly resists certain configurations. At ordinary scales, the resulting forces and quantum restrictions contribute to the familiar resistance we interpret as solidity. So when you place your hand on a wall, one of the deepest reasons your hand does not simply pass through it lies in the quantum behavior of electrons. The same particles whose stability initially seemed mysterious are responsible for much of the stability you experience in the macroscopic world. And again, no endless fuel supply is required. The table does not need to consume energy every second to prevent all its electrons from collapsing into lower states. Your body does not need to power the exclusion principle. These are simply features of the quantum laws governing matter. This distinction between a law and an active mechanism is easy to miss. In everyday life, when something is prevented from moving, we usually expect a force or barrier. A book does not fall through a table because the table exerts forces on it. A door remains closed because hinges and a frame constrain its motion. So when we hear that an electron cannot occupy some state, we imagine an invisible wall blocking it. But the Pauli exclusion principle is not a physical wall surrounding electrons. It is built into the mathematical structure, describing identical fermions. There is no hidden energy source enforcing it. Nature simply does not provide the forbidden configuration as an available state. This is similar to the ground state question. Why does the electron not keep losing energy below the ground state? Because there is no lower bound state available. Why do all the electrons in a many-electron atom not occupy exactly the same quantum state? Because quantum mechanics does not allow identical fermions to do so. Again and again, stability comes not from something continuously pushing matter into place, but from the structure of what states are physically allowed. This is a very different way of thinking about the universe. At the human scale, stability often feels active. A helicopter stays in the air because its rotors continuously transfer energy. Your body stays alive because metabolism continuously supplies usable energy. A refrigerator remains cold because electricity powers a process that moves heat. Stop supplying energy, and these systems change. But an electron does not need to be actively maintained as an electron. And a ground state atom does not need to be continuously powered to remain in its ground state. These are not machines operating far from equilibrium. They are stable configurations allowed by fundamental physics. This also helps explain why matter can persist for such extraordinary lengths of time. Consider a piece of rock floating alone in interstellar space. If it is not strongly heated, irradiated, or disturbed, many of its atoms could remain in their stable electronic configurations for enormous periods. There is no countdown timer inside each electron. The electrons are not gradually spending some limited reserve. An atom does not have a battery percentage. If the system remains in a stable state and nothing interacts with it strongly enough to produce a transition, there may simply be no reason for its electronic configuration to change. This is what makes the phrase, "the electron never runs out of energy," slightly misleading. It makes energy sound like a substance stored inside the electron. But an electron is not carrying a tank of energy that keeps its existence running. Energy is a property of physical states and systems. A free electron can have kinetic energy depending on its motion relative to an observer. An electron bound in an atom contributes to the energy of that atomic state. Interactions can transfer energy between particles and fields. But there is no universal amount of fuel inside an electron that is gradually depleted as the electron continues existing. The electron itself is astonishingly stable. As far as experiments have revealed, electrons do not spontaneously decay under ordinary conditions. They can participate in interactions. They can change momentum. They can become bound to atoms. They can leave atoms. They can annihilate if they encounter their antiparticle, the positron. But simply existing does not appear to consume them. An electron created billions of years ago is not an old, weakened version of an electron created today. There is no known aging process that slowly changes its electric charge or rest mass. Every electron appears fundamentally identical. This perfect identity is itself difficult to explain if we imagine elementary particles as miniature manufactured objects. Two cars of the same model are never truly identical. Two grains of sand differ microscopically. Even two atoms of the same isotope can occupy different states or environments. But elementary electrons share exactly the same intrinsic properties as far as we can measure. Modern quantum field theory gives us a deeper way to understand this. Instead of treating each electron as an independently manufactured little object, quantum field theory describes an electron field extending throughout the universe. What we call an electron is an excitation of that field. Every electron is associated with the same underlying quantum field. This is one reason their fundamental properties are identical. They are not separate miniature machines built according to the same blueprint. They are manifestations of the same underlying field. And this begins to transform our original question once again. We started by asking what keeps the electron moving. Then we discovered that it is not classically orbiting. We asked why it does not collapse into the nucleus and found that quantum confinement and the ground state prevent that classical picture. We asked why all electrons do not occupy the same lowest state and encountered the exclusion principle. Now we are beginning to see that even asking how an individual electron keeps itself alive may be based on the wrong image. Perhaps the electron is not a tiny object that must somehow maintain itself at all. Perhaps what we call an electron is a stable excitation of something deeper. And if that is true, then the next question becomes unavoidable. What exactly is the electron field? What does it mean for a particle to be an excitation of a field that exists everywhere? And why should that excitation be able to persist without slowly fading away? To understand why the electron itself does not seem to run out, we have to move one level deeper than the atom and enter the world of quantum fields. The deeper we look into the atom, the less the electron resembles the tiny object we first imagined. It is not a miniature planet circling a nucleus. It does not follow a hidden classical orbit. Its energy is not fuel being consumed as it moves. And even its remarkable identity begins to suggest that the electron may not be best understood as an isolated object at all. Every electron ever measured has the same electric charge, the same rest mass, the same spin, and the same fundamental behavior. An electron inside your body is not merely similar to an electron inside a distant star. As far as modern physics can determine, they are fundamentally indistinguishable. To understand why, we have to move beyond ordinary quantum mechanics and enter the framework that describes elementary particles at a deeper level, quantum field theory. In everyday physics, a field is something that has a value throughout space. The temperature in a room can be represented as a field because every location has a temperature. Earth's gravitational influence can be described using a gravitational field. The electromagnetic field tells us how electric and magnetic effects are distributed through space and time. Quantum field theory takes this idea much further. According to our best modern description of particle physics, fundamental particles are associated with quantum fields that exist throughout space. There is an electromagnetic field. There are quark fields. There are neutrino fields. And there is an electron field. The electron field does not exist only where electrons happen to be detected. It is part of the underlying physical description everywhere. What we call an individual electron can be understood as a quantized excitation of that field. This is difficult to visualize because there is no perfect everyday analogy. We might imagine waves appearing on an ocean where many different waves can arise from the same underlying body of water. But the electron field is not literally a material substance filling space, and an electron is not simply a classical ripple moving across it. Still, the analogy captures one useful idea. The particle and the field are not completely separate things. An electron is a manifestation of the electron field. This changes the way we think about the perfect identity of electrons. Imagine producing two identical metal spheres in a factory. However carefully we manufacture them, microscopic differences will remain. One may contain slightly different imperfections. Their atoms will occupy different arrangements. Their surfaces will never be exactly the same. If electrons were tiny, complicated objects manufactured somewhere in the early universe, their perfect similarity would be astonishing. Why would everyone have exactly the same charge, exactly the same rest mass, exactly the same spin? Quantum field theory offers a more natural answer. They are excitations of the same underlying field. An electron detected in a laboratory and an electron detected on the other side of the observable universe are not two independently designed machines that somehow happen to match perfectly. Their intrinsic properties arise from the same quantum field. And this gives us a new way to approach the question of why electrons do not run out of energy. The question originally made the electrons sound like a machine. A machine has components. Its components move. Friction and other processes dissipate useful energy. Eventually, the machine requires more energy, or it stops functioning. But as far as experiments have revealed, the electron has no known internal components. It is treated as elementary in the Standard Model. We have probed electrons at extremely small scales without finding a smaller structure inside them. This does not prove that no deeper structure could ever be discovered, but our current best theory does not require one. So there is no known internal engine to keep running. There are no gears, no microscopic parts rubbing together, no internal fuel supply. The electron does not need energy merely to continue being an electron. It is a stable quantum excitation, and stability is not the same thing as continuous maintenance. This distinction appears throughout fundamental physics. Consider a free electron moving through empty space. If nothing interacts with it, it can continue moving with constant momentum. It does not slowly lose speed simply because it has traveled for a long time. That statement is already familiar from classical mechanics. Motion itself does not consume energy. Energy is transferred when interactions occur. But quantum field theory takes the idea further. Even the existence of the particle does not require a continuous input of power. There is no universal background source constantly recharging electrons. The electron simply exists as an allowed excitation of the field. Its energy is part of its physical state. This does not mean an electron's energy can never change. Quite the opposite. Electrons interact constantly. Place an electron in an electric field, and it can accelerate. Let it interact with a photon, and energy and momentum can be exchanged. Bind it to an atom, and its possible energies become part of the atomic quantum structure. Supply enough energy, and the electron can be ionized from that atom. In a conductor, electrons participate in electrical currents. In stars, they scatter radiation and interact with ions inside hot plasma. The electron's state can change enormously, but the electron is not using up some internal substance every time it participates in an interaction. Energy moves between fields and particles. The electron remains an electron unless an interaction actually changes the particle content. There is one dramatic way an electron can disappear. If an electron encounters its antiparticle, the positron, the two can annihilate. Their energy and momentum can be transformed into other particles, often photons under suitable conditions. This is important because it shows that electrons are not indestructible in every possible sense. An electron can cease to exist through an allowed interaction. But this is completely different from slowly wearing out. The electron does not gradually weaken until it disappears. Its charge does not slowly decline. Its mass does not slowly evaporate away. Instead, particle physics allows specific interactions in which the initial particles are transformed into a different final state, while conserved quantities remain balanced. Without such an interaction, an isolated electron appears extraordinarily stable. In fact, no spontaneous electron decay has ever been observed. This is partly connected to the structure of the Standard Model and conservation laws. The electron is the lightest electrically charged lepton. For it to decay spontaneously into other ordinary particles, the final state would have to preserve electric charge while also respecting energy, momentum, and the relevant quantum rules. There is no lighter ordinary charged particle available into which the electron can simply decay. This creates another version of the pattern we saw inside the atom. A hydrogen atom, in its ground state, cannot continue releasing energy through lower electronic transitions because there is no lower electronic bound state. An electron does not simply decay into a lighter charged lepton because there is no such ordinary particle available. At two completely different levels, Stability emerges because there is nowhere allowed to go. This idea is worth holding on to. We often imagine stability as a battle. Something wants to collapse, decay, or disappear, while another mechanism continuously prevents it. But fundamental stability often looks different. A system can persist because the laws simply do not provide an accessible lower state or allowed decay process. Nothing needs to stand guard. Nothing needs to continuously spend energy. The stable configuration remains because it is stable. And this begins to explain why electrons can apparently survive for extraordinary periods. Some electrons around us may have participated in an enormous number of interactions throughout cosmic history. An electron could once have existed inside a cloud of plasma. Later, it could have become bound to an atom. That atom might have joined a molecule. The molecule could have become part of a dust grain. The dust could have entered a forming planetary system. The electron could later be ionized, captured again, transferred through chemical reactions, or move through an electrical circuit. Its quantum state could change again and again. But after every ordinary interaction in which an electron remains present, it is still an electron with the same fundamental intrinsic properties. It does not carry visible scars from its history. There are no young electrons and old electrons distinguished by their mass, no tired electrons, no electrons whose electric charge has faded after billions of years. Elementary particles do not appear to age in the way composite structures do. A human body ages because it is an incredibly complicated physical system. Cells accumulate changes. Molecular structures are damaged and repaired. Biological processes depend on continuous energy flows. Entropy and chemistry matter. A machine ages because its components change. A star ages because nuclear reactions alter its internal composition and the balance of forces within it. An electron has no known internal machinery undergoing an equivalent process. It can have a history of different quantum states, but its fundamental identity remains. This difference between elementary particles and complicated systems is one of the reasons our intuition fails so badly at the quantum scale. Everything we interact with in daily life is composite. A chair contains atoms. Atoms contain nuclei and electrons. Nuclei contain protons and neutrons. Protons and neutrons themselves contain quarks and gluons. At our scale, objects can break because their internal arrangements change. When we ask what prevents an electron from breaking down or running out of energy, we may be projecting the behavior of composite objects onto something that does not possess the same kind of internal structure. But quantum fields introduce another question. If the electron is an excitation of a field, could the field itself somehow be supplying the energy that keeps the electron alive? It is an appealing thought. Perhaps empty space contains some hidden reservoir continuously feeding particles. Perhaps the electron survives because the quantum vacuum constantly replenishes it. But this would again confuse having energy with consuming energy. The electron does not need to be continuously replenished because its existence is not continuously draining energy. Quantum fields possess ground states, and the lowest energy state of the fields is what physicists call the quantum vacuum. But the quantum vacuum is not an infinite battery from which particles can freely extract unlimited, usable energy. A ground state is, by definition, already the lowest energy configuration. There is nowhere lower for it to continuously fall while powering everything else. Still, the vacuum is far stranger than classical emptiness. Even when no ordinary particles are present, the quantum fields remain. Their lowest energy state has quantum structure, and interactions with those fields contribute tiny measurable corrections to the behavior of atoms and particles. One famous example appears in hydrogen. A simplified relativistic description predicts that certain atomic energy levels should coincide exactly. More complete quantum electrodynamics reveals a tiny difference known as the Lamb shift. Experiments measure this shift with extraordinary precision. The effect reminds us that the electron inside an atom cannot ultimately be understood in complete isolation from the quantum electromagnetic field. The atom is part of a deeper network of interacting fields, and yet the result is still not an electron being continuously refueled. Instead, the allowed energies of the complete quantum system reflect those interactions. The stable state already includes the relevant quantum physics. This is an important shift in perspective. We began by picturing an electron orbiting alone around a nucleus. Then the orbit became an orbital. The particle became a quantum state. And now even the particle itself becomes an excitation of an underlying field interacting with other fields. At every step, the image becomes less mechanical. There is less and less resemblance to a tiny machine that should eventually stop. And the question, where does the electron get the energy to keep going, begins to sound almost like asking where a kilogram gets the energy to keep having mass. Persistence is not automatically a process that consumes fuel. Some properties and states simply remain until an interaction changes them. But there is still one part of the atomic mystery we have not fully explored. If the electron's ground state is already the lowest energy state, what does lowest really mean? Why can't the energy keep decreasing forever? And why does quantum mechanics so often leave systems with some unavoidable energy, even when they have reached their minimum? The answer leads to zero-point energy, the quantum vacuum, and one of the strangest facts in physics. Even the lowest possible state of a quantum system is not necessarily the classical stillness we would expect. And understanding that will bring us even closer to the reason matter can remain stable without being continuously powered. The phrase ground state sounds simple. It is the lowest energy state available to a quantum system. Once an atom reaches it, there is no lower electronic state into which it can naturally transition. But hidden inside that simple statement is one of the deepest reasons stable matter can exist at all. The electron does not merely happen to stop losing energy at some convenient point. Quantum mechanics changes what a minimum energy state can be. At the smallest scales, reaching the lowest possible energy does not mean every form of motion disappears. Every uncertainty vanishes, and every particle becomes perfectly still. The quantum ground state is not the same thing as classical rest. To understand why, imagine something much simpler than an atom. Picture a ball sitting inside a curved bowl. If the ball is moving, friction eventually removes its kinetic energy. It rolls lower and lower until it reaches the very bottom. In the ideal classical picture, the final state is obvious. The ball sits exactly at the center of the bowl with exactly zero velocity. Its position is perfectly known. Its momentum is zero. Nothing prevents it from becoming completely motionless. Now imagine trying to create the quantum version of that situation. We want a particle to sit at one exact location with exactly zero momentum. Immediately, we encounter the uncertainty principle. Position and momentum cannot both be arbitrarily precise in a quantum state. The more tightly the particle is localized, the greater the unavoidable spread in its possible momentum measurements becomes. So the perfectly motionless classical ground state is no longer available. This becomes especially clear in a system physicists call the quantum harmonic oscillator. It is one of the most important models in all of quantum mechanics because versions of it appear throughout physics. Classically, an oscillator can have zero energy by sitting perfectly still at equilibrium. Quantum mechanically, the lowest possible energy remains above that classical minimum. This remaining energy is called zero-point energy. The system has reached its ground state, but its energy is not simply zero in the classical sense. This does not mean a tiny particle is secretly bouncing back and forth forever, like a microscopic spring. The ground state is a quantum state. Its unavoidable energy arises from the structure of quantum mechanics itself, and a related principle helps us understand the electron inside an atom. Suppose we tried to force the electron directly into an extremely tiny region around the nucleus. Doing so might seem attractive because the electron and nucleus have opposite electric charges. Bringing them closer reduces the electrostatic potential energy. If classical intuition were the whole story, perhaps the electron should simply collapse closer and closer toward the center. But localization has a price. As the region containing the electron becomes smaller, its position becomes more constrained. That means its momentum uncertainty must increase, and greater momentum spread means a larger kinetic energy contribution. So there is a competition. Electrostatic attraction favors bringing the electron closer to the nucleus. Quantum confinement makes squeezing it too tightly energetically expensive. The lowest total energy appears at a finite atomic size. This is one of the most beautiful examples of stability emerging directly from quantum mechanics. The electron does not hover at some distance because an invisible support holds it there. It is not orbiting fast enough to avoid falling. It is not being pushed outward by a mysterious source of energy. The quantum state with the lowest total energy naturally has a finite spatial extent. The atom has size because quantum mechanics gives it size. And once the atom reaches that lowest energy state, there is nowhere lower for it to go through an ordinary electronic transition. This allows us to answer an important version of our original question. Could the electron eventually lose all of its energy? Not in the way the question suggests. If an electron is bound inside an atom, we should really speak about the energy of the quantum state of the entire system. The electron and nucleus interact. Their potential and kinetic contributions combine into a total atomic energy. The ground state is the minimum of that total. There is no continuous staircase extending downward forever. If there were, matter would have a serious problem. Imagine a universe in which every time an atom released energy, another slightly lower bound state always existed. The electron could fall into that state and release more energy. Then another state would appear below it, then another. There would be no true bottom. Atoms might continually release energy while becoming more compact, with no stable endpoint. Our universe instead provides ground states. Energy spectra are bounded below. That phrase, bounded below, sounds technical, but its physical consequence is enormous. There is a floor, and a universe containing floors can build stable structures. Once an atom reaches its ground state, it does not need a constant energy source to keep it there. In fact, adding energy is what can disturb it. Shine a photon with an appropriate energy onto the atom, and the photon may be absorbed. The atom moves into an excited state. Now a lower state is available. The system can transition downward again and emit energy. Eventually it returns to the ground state. Then the ordinary downward process ends. The ground state is therefore not like an engine idling at minimum power. It is more like the bottom of the allowed energy landscape. Nothing has to continually provide energy to stop the system from descending, because no lower ordinary electronic destination exists. This is also why the phrase electron running out of energy can cause so much confusion. Energy is not a substance inside the electron that gradually leaks away with age. When physicists say an electron has energy, the meaning depends on the situation. A free electron can have kinetic energy relative to an observer. An electron in an electromagnetic field can have energy associated with its state and interactions. An electron bound inside an atom participates in a quantum state with a definite total energy. These quantities can change when interactions transfer energy, but the electron does not have a fuel gauge. Imagine an electron in empty space moving freely. If it is completely isolated, it does not need to burn energy to maintain constant velocity. Now imagine an electron bound in the ground state of hydrogen. It likewise does not need to burn energy to remain in that stationary quantum state. These are different physical situations, but they share the same important principle. Energy is not automatically consumed by persistence. There must be a physical process transferring it somewhere else. This raises a useful question. When does an electron actually lose energy? One example occurs when a free electron is accelerated or decelerated in certain ways and electromagnetic radiation is emitted. Another occurs in atomic transitions, where the energy of the overall atomic system decreases, and a photon carries away the difference. But these are specific interactions and changes of state. They are not evidence that the electron constantly loses energy simply by existing. This distinction explains why an excited atom can radiate while a ground state atom remains stable. The excited state has lower energy states available. The ground state does not. Imagine two atoms sitting next to each other. One is in its ground state. The other has absorbed energy and entered an excited state. The excited atom may later emit a photon and transition downward. The ground state atom can simply remain as it is. Time passing is not enough to force it to release energy. There is nothing available for it to release through a lower electronic transition. This is profoundly different from many familiar systems. A hot cup of coffee loses thermal energy because it interacts with a cooler environment. A spinning wheel slows because friction transfers energy into heat. A satellite in a very low orbit can lose orbital energy because it interacts with the thin atmosphere. In each case, there is a mechanism carrying energy away. If we remove that mechanism, the continuous loss disappears. We often forget this because almost nothing in everyday life is perfectly isolated. Friction surrounds us. Air resistance surrounds us. Heat constantly moves between systems. Living things continuously transform chemical energy. Our intuition, therefore, becomes trained to associate activity with energy consumption. At the quantum level, that association can fail completely. An electron does not have to pay an energetic price simply for another second of existence, and an atomic ground state does not need to be recharged. But there is an even stranger implication. The lowest energy state can still contain structure. The electron in hydrogen's ground state is not located at one exact point. It has a spatial probability distribution. The state has kinetic energy. The electron and proton remain electromagnetically bound. The atom has a characteristic size. So, minimum energy does not mean nothingness. It does not mean every physical property disappears. A ground state can be rich with quantum structure. This becomes even more dramatic when we move from individual particles to quantum fields. In quantum field theory, each field also possesses a lowest energy state. That state is called the vacuum. The word vacuum makes us imagine complete emptiness. Remove every particle, every atom, every photon, every molecule, and eventually nothing remains. But the quantum vacuum is not philosophical nothingness. The fields themselves still exist, and their ground state retains quantum properties. This is where popular descriptions sometimes become misleading. You may have heard that empty space is filled with particles, constantly appearing from nothing and disappearing again. That image can occasionally be useful as informal language for certain calculations, but taken literally, it creates the wrong picture. The deeper statement is that quantum fields in their vacuum state possess irreducible quantum structure and fluctuations in observables. The vacuum is a physical quantum state, and some consequences of quantum vacuum physics are measurable. The Casimir effect provides a famous example. Place two conducting surfaces extremely close together under suitable conditions, and the electromagnetic field configurations allowed between and outside the surfaces differ. This produces a measurable force. Atomic physics provides another. The interaction between an electron and the quantized electromagnetic field slightly modifies atomic energy levels. The Lamb shift, which we encountered earlier, is one measurable result. So even the lowest energy state of the fields is not identical to classical empty nothingness. But this does not mean the vacuum is continuously feeding energy into electrons. That idea would bring us back to the same misconception. The electron does not need continuous feeding because it is not continuously losing energy, merely by existing. And the vacuum is itself a ground state. Calling it a source of unlimited free energy would misunderstand what a ground state means. If a system is already in its lowest energy state, you cannot repeatedly extract useful energy by pushing it into endlessly lower states that do not exist. There is no infinite basement beneath the basement. Again, the floor matters. And this pattern appears throughout the physics we have explored. The hydrogen atom is stable because its electronic energy has a minimum. Quantum oscillators possess ground states. Quantum fields possess vacuum states. The electron itself appears stable because there is no known ordinary, allowed decay into a lighter charged particle. At each level, stability is closely connected to the structure of allowed states. Nature does not need to continuously spend energy to enforce these structures. They are part of the laws. This is perhaps the deepest correction to the original mental image. We began with a tiny electron racing endlessly around a nucleus and wondered what fuel could possibly keep it moving. But there is no engine. There is no fuel. There is no classical orbit. There is a quantum state whose lowest energy configuration is stable. And once the electron is in that state, asking where the energy comes from to keep it there is almost backwards. Energy would be required to take it out. This is why atoms can survive. It is why matter can remain structured, and it is one reason the universe does not immediately collapse into a featureless state. But there is another side to this stability that we have not yet explored. Electrons do not merely sit inside isolated atoms. They move through metals. They carry electric current. They absorb and release energy. They participate in chemical reactions and interact with radiation. Inside your computer, enormous numbers of electrons participate in electrical processes every second. Inside stars, electrons exist in hot plasma and undergo constant collisions. If electrons can exchange energy so freely, why don't those interactions eventually wear them down? Why can an electron participate in countless processes and still emerge as exactly the same fundamental particle? To answer that, we need to separate the energy an electron can gain or lose from the identity of the electron itself. An electron can gain energy. It can lose energy. It can accelerate through an electric field, collide with other particles, absorb energy from radiation, become trapped inside an atom, escape from that atom, and later become bound somewhere else. Inside matter, electrons participate in an almost unimaginable number of interactions. And yet, after all of this, an electron remains an electron. It does not become weaker because it has transferred energy too many times. Its electric charge does not slowly fade. Its rest mass does not decrease with age. There is no known point at which an electron has simply been used too much and can no longer function. To understand why, we have to separate two things that everyday experience encourages us to combine: the energy associated with a particle's state and the identity of the particle itself. Imagine an electron moving freely through space. Relative to you, it may possess kinetic energy. If an electric field accelerates it, that kinetic energy can increase. If it later interacts with matter and transfers some of that energy, its kinetic energy can decrease. But the electron itself has not been partially consumed. Its state changed. Now consider an electron bound inside an atom. Its energy is described as part of the quantum state of the entire atomic system. Supply the correct amount of energy, and the atom can become excited. Supply enough, and the electron can be removed entirely. Again, the electron does not become a different, weaker electron. It has entered a different physical state. This distinction becomes especially clear in electrical circuits. When you switch on a lamp, electrons inside the wires participate in the electrical current. It is tempting to imagine the power station or battery filling those electrons with energy and sending them racing through the wire until they arrive at the lamp exhausted. That is not a good picture of what happens. The electrons in the conductor are already present. When an electric field is established, charges respond to that field. Energy is transferred through the electromagnetic system and ultimately transformed into other forms inside the device. In a traditional incandescent bulb, electrical energy eventually becomes large amounts of thermal energy and visible radiation. In an LED, electronic transitions within the semiconductor produce light through a different mechanism, but the electrons are not burned as fuel. After participating in the current, they remain electrons. The source provides energy to the system. It does not provide replacement existence to the electrons. The same is true inside your computer. Vast numbers of electrons participate in electrical processes while information is processed. Their states and collective behavior are manipulated with extraordinary precision, but the individual electrons do not gradually disappear because the processor has completed too many calculations. If they did, electronics would work very differently. Eventually, every wire would contain exhausted particles that needed to be replaced. Nothing like this occurs, and the same principle extends far beyond technology. Inside the sun, matter exists largely as plasma. Electrons are no longer neatly bound to individual atoms throughout much of the interior. They move through an environment filled with nuclei, radiation, electromagnetic fields, and constant collisions. Temperatures are enormous. Energy is exchanged continually. Photons interact with charged particles. Electrons change momentum again and again. Yet the sun's electrons are not slowly being consumed by all this activity. The sun does lose energy, of course. It radiates an enormous amount into space every second. But that energy ultimately comes from changes in nuclear configurations during fusion, not from electrons gradually using up their own existence. The electrons participate in the plasma. They are not the fuel tank. This is the same mistake we made with the atom, now appearing on a larger scale. We see something active and assume the particles involved must be spending themselves. But energy transfer does not require the destruction of the object participating in the transfer. A tennis racket can transfer energy to a ball without disappearing. A gravitational field can change the kinetic energy of an object without being a fuel in the ordinary sense. And an electron can transfer energy and momentum through interactions without becoming less of an electron. At the quantum field level, this becomes even clearer. An electron is an excitation of the electron field with a particular set of intrinsic properties. Its electric charge is not a quantity that slowly leaks out during ordinary interactions. Its rest mass is not a reservoir from which normal atomic processes continuously withdraw tiny pieces. Those properties characterize what an electron is. Of course, mass itself is related to energy through Einstein's famous relation between mass and energy. But this does not mean an isolated electron is continuously converting its rest mass into fuel just to survive. Its rest energy is part of the energy associated with the particle. It does not need to be consumed to maintain the particle from one second to the next. This becomes easier to appreciate when we compare an electron with an unstable particle. Consider the muon. A muon resembles a much heavier cousin of the electron. It has the same magnitude of electric charge and belongs to the same broader family of particles, but it is far more massive. And unlike the electron, a free muon is unstable. After an average lifetime of roughly 2.2 microseconds in its rest frame, it decays into other particles. The muon does not decay because it has been moving too long and runs out of energy. It decays because the laws of particle physics permit a transition from the muon state into a set of lighter particles while respecting the relevant conservation laws. The decay is an allowed physical process. The electron is different. It is the lightest charged lepton. There is no lighter charged lepton beneath it into which it can simply decay while preserving electric charge in the ordinary standard model. This gives the electron an extraordinary kind of stability. Again, the reason is not active maintenance. There is no mechanism constantly repairing the electron before it decays. The ordinary decay channel simply is not available. This repeats the pattern we encountered with the atomic ground state. An excited atom can transition downward because lower energy states exist. Eventually, it reaches the ground state. Then there is no lower bound electronic state into which it can continue radiating. A muon can decay because allowed lighter final states exist. An electron cannot undergo an analogous ordinary decay because the necessary lower charge state is absent. At both levels, stability appears because the system has reached a kind of bottom. This may be one of the most important ideas in the entire video. Things do not always persist because something is continuously keeping them alive. Sometimes they persist because there is no allowed process that makes them stop. This feels unfamiliar because human life is almost the opposite. Your body requires continuous energy. Even while you sleep, cells maintain concentration gradients, repair structures, synthesize molecules, pump ions across membranes, regulate temperature, and perform countless chemical reactions. You are not a static ground state. You are a tremendously complicated system maintained far from thermodynamic equilibrium. Stop the flow of usable energy, and that organization cannot persist indefinitely. A machine behaves similarly. An airplane remains in controlled flight because engines and aerodynamic forces continuously interact. A computer requires electrical power to perform computation. A refrigerator requires energy to maintain a temperature difference between its interior and surroundings. These systems require energy because processes are being actively maintained. An electron is not that kind of system. There is no known metabolism of the electron, no internal temperature that must be regulated, no molecular structure that must be repaired, no moving components slowly damaged by friction. As far as current experiments can determine, the electron is elementary, and that means our ordinary concept of aging does not translate naturally to it. Imagine two electrons. One was created moments ago in a high-energy particle interaction. The other has existed since the early universe. If we prepare them in the same quantum state, there is no known experiment that could tell which one is older by examining some accumulated wear inside the particles. Their charge is identical. Their rest mass is identical. Their spin is identical. There is no microscopic aging mark. This is very different from macroscopic objects. Take two cars of the same model, one new and one driven for 20 years, and their histories become visible in their physical structures. Take two stars of different ages, and their internal compositions may reveal where they are in their evolution. Take two human beings of different ages, and countless biological differences emerge. Elementary electrons do not appear to preserve their histories in this way. Their past can affect their current quantum state, position, momentum, or relationships with other systems, but it does not appear as wear in the fundamental electron itself. And this means an electron could, in principle, participate in one interaction after another across enormous spans of cosmic history without becoming progressively exhausted. It might be accelerated, then scattered, then captured by an atom, then released, then incorporated into a molecule, then transferred through a chemical reaction, then sent through an electrical circuit. Its state could change dramatically each time. But whenever the process leaves an electron in the final state, that electron has the same fundamental intrinsic properties as any other electron. There is something almost unsettling about this perfect persistence. The universe around the electron can transform completely, while the electron remains fundamentally unchanged. A star can collapse. A planet can form. A molecule can break apart. A civilization can build a machine and use that electron inside a circuit. Structures appear and disappear. The fundamental particle does not become tired from participating in them, but we should be careful not to turn this into the claim that electrons are absolutely indestructible. As we saw earlier, an electron can encounter a positron and annihilate. The electron and positron disappear as those particles, while their energy and other conserved quantities are carried into the products of the interaction. So the correct statement is not that an electron can never cease to exist. It is that it does not naturally wear out simply because time passes or because it has participated in ordinary interactions. Destruction requires an allowed physical process. Age alone is not enough. And this reveals the central difference between energy loss and particle destruction. An electron can lose kinetic energy and remain an electron. It can move from a higher energy atomic state to a lower energy configuration while remaining part of the system. It can transfer energy to radiation. It can receive energy from radiation. Its energy can change without its identity disappearing. The electron is not its kinetic energy. It is not its atomic energy level. It is not the energy it happens to carry relative to a particular observer. Those are properties of its physical state. This is why asking when the electron will run out has no simple meaning. Run out of which energy? A free electron could be at rest relative to you, and therefore have zero kinetic energy in that frame, yet it would still exist. An electron in an atom could be in the lowest energy electronic state and still exist. Reducing the energy of a state does not mean gradually erasing the particle. The electron does not require a minimum supply of kinetic energy to remain real. And this is perhaps the point where the original mystery finally begins to dissolve. We imagined the electron as something that must keep moving in order to avoid falling into the nucleus. Then we imagined that movement must require energy. Then we assumed that energy must eventually be exhausted. Every step followed naturally from everyday experience, and almost every step was wrong. The electron does not orbit classically. Constant motion does not inherently consume energy anyway. The bound electron occupies quantum states. The atom has a ground state. The electron itself is a stable excitation of a quantum field, and ordinary changes in energy do not consume the electron. What looked like an impossible perpetual motion machine was never a machine at all. But there is one more piece of the puzzle. If electrons can remain stable and atoms can remain in their ground states, why does the world around us change so much? Why does matter heat up, cool down, react, conduct electricity, emit light, and transform if its fundamental particles are so stable? The answer lies in the difference between stable ingredients and changing arrangements. And that distinction is what allows a universe built from persistent particles to become a universe filled with stars, chemistry, life, and constant change. If electrons can remain fundamentally unchanged for enormous spans of time, and atoms can settle into stable ground states without constantly consuming energy, then the universe seems as though it should become strangely static. Stable particles should create stable atoms, and stable atoms might seem to suggest a world in which very little happens. Yet reality is almost the exact opposite. Stars burn. Matter changes temperature. Molecules form and break apart. Electricity flows. Planets evolve. Living organisms grow, reproduce, and eventually die. The universe is filled with change, even though many of its fundamental ingredients are remarkably persistent. The reason is that stable ingredients do not require stable arrangements. An electron can remain an electron while changing almost everything about its relationship to the world around it. It can occupy one atomic state and later another. It can be bound to an atom and then become free. It can move through a conductor. It can participate in chemical bonds. It can exchange energy and momentum with photons and other particles. The electron persists. The configuration changes. And this distinction between fundamental identity and changing arrangement is one of the keys to understanding how a universe made from stable particles can still be dynamic. Consider something as ordinary as heating a piece of metal. When the metal becomes hotter, we are not creating a new kind of electron. The electrons do not become fundamentally hotter particles with different intrinsic masses or charges. Instead, energy is redistributed among the enormous number of particles and collective excitations making up the material. Atoms vibrate more strongly. Electrons occupy and move among available states differently. Interactions transfer energy throughout the material. Eventually, if the metal is allowed to cool, energy leaves the system and enters the surroundings. The fundamental particles remain. What changes is their state and organization. The same idea appears in chemistry. Imagine hydrogen reacting with oxygen to form water. The electrons involved do not disappear and get replaced with special water electrons. Instead, the nuclei and electrons reorganize into a new molecular configuration. The energy of that configuration differs from the energy of the initial arrangement. Chemical bonds form. Energy can be released. The same basic particles now participate in a different structure. This is what chemistry largely is: the rearrangement of electrons and atomic nuclei into new quantum configurations. The extraordinary diversity of the material world does not require an extraordinary diversity of fundamental particles. It requires an extraordinary diversity of arrangements. Carbon provides perhaps the most familiar example. The same carbon atoms can participate in graphite, diamond, biological molecules, carbon dioxide, and countless other substances. The carbon nuclei do not need to become different fundamental objects in each case. Their electrons do not need new intrinsic properties. What changes is the arrangement. Quantum states and bonds change, and entirely different macroscopic properties emerge. A soft material and an extremely hard material can therefore arise from the same element. This teaches us something important about energy. When a chemical reaction releases energy, the electrons are not releasing the fuel they require in order to continue existing. The entire physical system is moving from one arrangement to another with a different total energy. The difference can appear as heat, light, motion, or other forms of energy. The particles survive the transition. This is why we can repeatedly rearrange matter without using up its electrons. An electron inside one molecule can later become associated with another molecule. It may participate in thousands or millions of chemical interactions over time. It does not contain a limited number of reactions before it stops working. Again, there is no electron battery percentage. The energy belongs to states and interactions. This distinction becomes even more dramatic inside stars. The sun radiates roughly unimaginable quantities of energy into space, and it has been doing so for billions of years. If we approach this with the same intuition that originally confused us about electrons, we might imagine that the particles inside the sun are gradually using up their own energy simply by moving and colliding. But the main source of the sun's long-term energy is nuclear fusion. Deep inside the core, hydrogen nuclei participate in processes that ultimately produce helium. The final configuration has slightly less mass energy than the initial ingredients, and that difference appears in other forms of energy. The particles and fields in the solar interior then redistribute that energy through countless interactions. Electrons participate constantly. They scatter. They interact electromagnetically. Their momenta and energies change. But the electron itself is not the fuel being burned. Eventually, some of the energy reaches the surface and escapes as a radiation. A photon may leave the sun and cross space until it reaches Earth. It might be absorbed by a solar panel. There, its energy can help produce electrical effects involving electrons in the material. Those electrons can then participate in an electric current. The energy has traveled through a chain of transformations. Nuclear energy inside the sun, radiation, electromagnetic interactions in the solar panel, electrical energy in a circuit, perhaps eventually light from a screen. Throughout this chain, electrons participate in the transfer without being continuously consumed. This is what conservation of energy really allows. Energy does not need to remain attached to one particular particle. It can move between different parts of a system and appear in different forms. An electron can gain kinetic energy and later transfer it. An atom can absorb a photon and become excited, then emit another photon as it relaxes. A molecule can store chemical energy and later release it through a reaction. The total bookkeeping remains consistent, even though the local arrangements constantly change. And this gives us a more precise answer to the question of where an electron gets its energy. There is no single answer, because an electron does not possess one fixed amount of usable energy throughout its existence. Its energy depends on the physical situation. A free electron's kinetic energy depends on its motion relative to the observer. An electron bound in an atom participates in discrete atomic energy states. An electron inside a solid participates in a much more complicated collective quantum system. Interactions can change those energies, but none of this determines whether the electron continues existing. This is why the phrase "never runs out of energy" is useful as a mystery, but dangerous as a literal physical description. The electron can absolutely lose energy. What it does not do is lose some necessary supply of existence energy until it eventually stops being an electron. If an electron transfers kinetic energy and ends up at rest relative to you, it still exists. If an atom releases energy and reaches its ground state, the electron still exists. The electron can reach a state from which no more energy can be extracted through a particular process without somehow disappearing. The lowest energy available to the system is still a physical state. This is deeply different from fuel. When a fuel tank reaches zero, the engine can no longer perform the process that required the fuel. When an atom reaches its ground state, it has not lost the ability to exist. It has reached stability. And this gives us a useful way to distinguish equilibrium from activity. Many systems in the universe naturally evolve toward lower energy or higher entropy configurations. A hot object cools because energy spreads into its surroundings. An excited atom can decay because a lower energy state is available. A chemical reaction may proceed because the resulting arrangement is energetically and statistically favored under the relevant conditions. But once a system reaches a stable equilibrium state, continuous energy expenditure is not necessarily required to keep it there. In fact, continuous energy input may be required to move it away from equilibrium. Life is an extraordinary exception in this sense. A living organism maintains highly organized processes far from equilibrium. Your cells constantly move ions, build molecules, break molecules apart, repair structures, and preserve concentration differences. This requires a continuous flow of usable energy. stop that flow, and the organization eventually breaks down. But the atoms themselves remain, the electrons remain, the molecules may rearrange, but the elementary particles are not destroyed simply because biological organization ends. The pattern requires energy. The ingredients do not. This may be one of the deepest ways to understand the difference between fundamental matter and the complicated world built from it. A pattern can be temporary even when its ingredients are stable. A wave on the ocean disappears, but the water remains. A cloud forms and dissolves, while the molecules continue. A living organism exists for a limited time, while many of its atoms existed long before it and may continue long afterward. A star shines for billions of years and eventually changes dramatically, while many of the electrons involved can persist through the entire process. The universe constantly builds temporary structures from persistent ingredients, and those structures can become extraordinarily complicated. Stable electrons allow stable atoms. Stable atoms allow molecules. Molecules allow chemistry. Chemistry allows planets with oceans, atmospheres, minerals, and complex organic compounds. Under the right conditions, chemistry becomes organized into systems capable of maintaining themselves through energy flow. Eventually, at least here on Earth, some of those systems became capable of perception, then memory, then thought, and eventually physics. Matter organized itself into something capable of asking why matter is stable. There is something remarkable about that chain. The electron does not know it is inside a neuron, rather than a distant star. It does not acquire a different charge because it becomes part of a brain. The same quantum rules continue operating, yet enormous collections of those simple, stable ingredients can produce properties that no individual electron possesses. A single electron is not wet. A single electron is not alive. A single electron does not think, but arrange electrons, nuclei, and fields in particular ways, and new levels of behavior emerge. This is emergence, and emergence depends on stability. If fundamental particles constantly wore out or randomly changed their intrinsic properties, complex structures would be extremely difficult to preserve. Imagine if electrons gradually lost charge as they aged. Chemistry would change with time. Old atoms would behave differently from new atoms. The periodic table would not provide the reliable foundation we observe. Molecules might slowly become unstable for reasons unrelated to their environment. Instead, electrons appear astonishingly consistent. The laws that govern them today appear to have governed matter throughout cosmic history. We know this partly because of light from distant objects. When astronomers observe ancient galaxies, they see atomic spectral signatures produced billions of years ago. Those signatures reveal the same underlying quantum structure. Hydrogen in the distant universe behaves like hydrogen here. Electrons there obey the same fundamental rules. This consistency is one reason physics can reconstruct cosmic history at all. The universe changes while its underlying laws remain remarkably stable. But stable ingredients do not guarantee that every structure lasts forever. Atoms can be ionized. Molecules can break. Stars can explode. Planets can be destroyed. Even protons may or may not ultimately be absolutely stable. Some theories beyond the standard model predict proton decay, although it has never been observed. The important point is that change occurs through physical processes. Things do not simply wear away because existence itself has an unavoidable energy cost. And electrons provide perhaps the cleanest example. An electron can exist. It can interact. Its state can change. It can transfer energy. And then it can continue existing without needing to recharge. This brings us very close to resolving the mystery completely. But one strange question remains. If electrons do not wear out, could an electron theoretically survive forever? Could an electron created in the early universe still exist after stars disappear, galaxies fade, and the cosmos becomes unimaginably old? And if the universe eventually approaches a state with almost no usable free energy left, would electrons themselves somehow stop? The answer forces us to separate the lifetime of a particle from the lifetime of the structures around it, because the far future of the universe may become dark, cold, and almost empty. Stars may eventually cease shining. Complex structures may disappear. Usable energy may become increasingly difficult to extract. Yet that does not necessarily mean the electron itself runs out of anything. And following that idea into the distant future reveals just how different fundamental stability is from the temporary world built on top of it. Imagine following a single electron far beyond the timescales of human history, not for a century or a million years, but through the entire future evolution of the cosmos. Civilizations disappear, continents shift, and planets change. The sun exhausts the fuel in its core and evolves away from the star we know today. Long after that, other stars continue shining until eventually they too reach the ends of their lives. Star formation becomes increasingly rare as usable gas is consumed or locked away. The universe grows darker. Galaxies change. Stellar remnants remain. And cosmic expansion continues, carrying distant regions farther apart. Through all of this, could the same electron simply continue to exist? Could a fundamental particle survive while almost everything built from particles disappears? As far as modern experiments can tell us, there is no known maximum age for an electron. No spontaneous electron decay has ever been observed. This does not allow physics to prove that every electron must literally exist forever. Future discoveries could reveal processes not included in our current theories. But within the standard model, the electron is treated as stable. And the reason, again, has nothing to do with an endless supply of energy. An electron does not survive because the universe keeps charging it. It survives because there is no known ordinary decay process available to it. To appreciate how unusual this is, compare the electron with other particles. A free neutron is unstable. Remove a neutron from most atomic nuclei, and on average, it survives for only around 15 minutes before undergoing beta decay. In that process, the neutron transforms into a proton, while an electron and an antineutrino are produced. A muon is even shorter lived. It survives for only about 2.2 microseconds on average in its own rest frame before decaying. Many particles discovered in high-energy physics exist for extraordinarily tiny fractions of a second. Their disappearance is not caused by exhaustion. They decay because the laws of physics allow them to transform into lower energy combinations of particles while respecting the necessary conservation laws. The electron occupies a different position. It is the lightest charged lepton. If an electron were to spontaneously decay, electric charge would still need to be conserved. Whatever emerged would somehow need to account for the electron's negative electric charge while also satisfying the other relevant conservation laws and having a total energy compatible with the original electron. Within the standard model, there is no lighter charged lepton waiting beneath the electron, so the ordinary decay staircase stops. Once again, nature reaches a floor. This is almost exactly the pattern we encountered inside the atom. An excited atom can release energy because a lower state exists. The atom reaches its ground state, and the ordinary downward electronic transitions stop because there is nowhere lower to go. A muon can decay because lighter allowed final states exist. The electron does not have an equivalent ordinary decay available. At one level, an atomic state is stable. At another, the fundamental particle itself is stable. And in neither case does stability require continuous power. This becomes particularly interesting when we imagine the far future of the universe. The universe is filled with usable energy today because enormous differences exist everywhere. Stars are hot while surrounding space is cold. Matter can fall through gravitational fields. Chemical systems can move toward lower energy configurations. Nuclear reactions can release energy. Temperature differences can drive processes. Life itself depends on these kinds of differences. Earth receives relatively concentrated energy from the sun, and ultimately radiates lower temperature energy back toward space. Biological systems exploit energy flows along the way. But thermodynamics tells us that usable energy differences tend to become less available as systems approach equilibrium. This is connected to entropy. Entropy is often casually described as disorder, but that word can be misleading. More precisely, Entropy relates to how many microscopic configurations correspond to a macroscopic state, and to the direction in which energy tends to spread among available degrees of freedom. A hot object in a cold room cools because energy spreads. You do not normally see the room spontaneously transfer enough random thermal energy back into the object to make it hot again. The microscopic laws allow many processes, but overwhelmingly probable macroscopic evolution produces the familiar thermodynamic arrow of time. Now imagine this process extended to cosmic scales. If the universe continues expanding for an extremely long time, stars will not shine forever. The supply of ordinary stellar fuel is finite. Existing stars eventually evolve. New stars become rarer. White dwarfs, neutron stars, black holes, and other remnants dominate increasingly ancient cosmic environments. On timescales almost impossible to comprehend, the universe may become extraordinarily dark and dilute. This general picture is often associated with the idea of heat death. The phrase sounds as though the universe somehow reaches zero energy, but that is not what it means. Energy can still exist. Particles can still exist. What disappears is the easy availability of useful energy, differences capable of driving complex processes. This distinction is essential. A universe approaching thermodynamic equilibrium does not necessarily contain no energy. It contains less free energy available for organized work. Imagine an ocean of water at one uniform temperature. The water still contains enormous microscopic thermal energy. Molecules continue moving, but without a useful temperature difference, extracting work becomes much more difficult. The problem is not the absence of energy, it is the absence of a gradient. And an electron in such a universe would not suddenly stop existing because there was no longer enough useful energy around it. The electron does not need the universe to provide power for its existence. It could occupy a low energy state and simply remain. This creates an extraordinary image of the distant future. The complex structures built from matter may be temporary. Stars are temporary. Planets are temporary. Molecules may be temporary on sufficiently long timescales. Even galaxies as recognizable structures may not remain forever in their current forms. But some fundamental particles could potentially outlast almost all of them. The ingredients may survive their creations. An electron that once participated in a living cell could later become part of soil. It might eventually become part of another molecule. Much later, astronomical processes could carry it elsewhere. Perhaps the planet containing it is transformed when its star evolves. Perhaps the electron becomes part of ionized material expelled into space. Perhaps it travels freely for an enormous period before becoming bound again. There is no fundamental label attached to it recording that history. It does not remember being part of a cell. It does not remember a planet. It does not remember a star. Its current quantum state contains the physically relevant information about its present situation, while its intrinsic properties remain those of an electron. This is one of the strangest differences between fundamental particles and the structures they create. Complex structures preserve history. A tree contains evidence of how it grew. A rock can preserve information about geological processes. Light from distant galaxies carries information about ancient cosmic events. Your brain physically encodes memories through complex changing structures. But an elementary electron does not appear to accumulate an internal record of its age. An ancient electron is not wrinkled. It does not become slower because it has existed for billions of years. It does not require increasing amounts of energy to keep itself stable. If two electrons are prepared in identical quantum states, quantum mechanics treats them as fundamentally indistinguishable. In fact, indistinguishability goes deeper than simply being unable to tell them apart with our instruments. Identical quantum particles are described in a way where assigning permanent classical identities to them can lose physical meaning. In ordinary life, if two identical-looking balls cross paths, we assume there is always a fact about which ball is which. We may lose track of them, but the identity remains. Quantum particles are stranger. Identical electrons are not merely objects whose identifying marks are too small for us to detect. They are fundamentally identical excitations of the same electron field. This makes the question, is this exactly the same electron, more subtle in quantum systems, involving many identical particles than it would be for classical objects? But the larger point remains. Electron excitations do not appear to wear out, and this means the end of useful energy in the universe would not automatically mean the end of electrons. There is an important distinction here between energy and free energy. The universe does not need to run out of energy for stars and life to become impossible. It only needs to approach conditions where energy is distributed in ways that no longer provide the gradients necessary to power complex processes. A star needs an imbalance. Life needs an imbalance. A machine needs an imbalance. An electron does not. It can exist in equilibrium. This reveals why our original intuition was so misleading. We are living systems, and everything about our existence depends on energy flow. You need food because your body constantly performs work. Your cells need chemical-free energy because they actively maintain organized states. Your brain requires metabolism because thoughts correspond to physical processes that consume and redistribute energy. When the usable energy flow stops, the organized process we call life cannot continue. So when we imagine an electron existing for billions of years, we naturally ask what it has been eating. What keeps it powered? What keeps it moving? What prevents it from becoming exhausted? But those questions apply the logic of a living, non-equilibrium system to a fundamental particle. The electron does not need to maintain a complicated internal organization against thermodynamic decay. As far as we know, there is no internal machinery to maintain. Its existence is not a continuous act of resistance against entropy. It is simply an allowed state of the quantum field. And this gives us a much cleaner way to think about the possible future of an electron. If the electron remains stable under the fundamental laws, time alone does not destroy it. A billion years does not weaken it. A trillion years does not necessarily weaken it. The number of interactions it has experienced does not gradually subtract from some fixed lifetime allowance. Only an actual physical process capable of transforming or annihilating it can end its existence as an electron. One such process, as we have seen, is interaction with a positron. If an electron and positron meet under appropriate conditions, they can annihilate, and their energy can emerge in other forms. That electron is gone, but it did not die of old age. It participated in an interaction allowed by quantum field theory. This difference is crucial. A stable particle can still be destroyed. Stability does not mean invulnerability. It means there is no spontaneous, ordinary decay that inevitably occurs after some characteristic lifetime. And that brings us back to the atom. An atom in its ground state is stable, but a sufficiently energetic photon can ionize it. A stable molecule can still be broken apart by an interaction. A stable planet can still be destroyed by a collision. Stability always exists within the context of possible processes. Nothing needs to decay spontaneously, simply because time passes. And perhaps this is the deepest lesson hidden inside the question of whether an electron can exist forever. Time itself is not a corrosive substance. Things do not necessarily deteriorate merely because more seconds have passed. They change because physical processes occur. Human beings age because biological processes unfold. Mountains erode because they interact with wind, water, temperature changes, gravity, and chemistry. Stars age because nuclear reactions alter their internal structure. Machines wear because their materials experience friction, stress, chemical reactions, and other physical changes. Time allows those processes to occur, but time is not itself the mechanism doing the damage. For an electron, there is no known internal aging process waiting to accumulate. And so the electron exposes something almost philosophical about persistence. Perhaps nothing needs an explanation for why it continues existing from one moment to the next in the way we instinctively imagine. Perhaps what requires explanation is change. If the laws permit a stable state and no interaction disturbs it, persistence is simply what happens. The electron does not need to continuously earn another second of existence. It remains until physics gives it a reason not to. And this finally brings us to the deepest version of our original question. We began by asking why an electron never runs out of energy. But now we can see that the question contains an assumption we no longer need. An electron does not require a continuous supply of energy simply to exist. An atom does not require fuel to remain in its ground state. Matter is not held together by microscopic engines constantly fighting collapse. Its stability comes from quantum states, uncertainty, exclusion, conservation laws, and the structure of quantum fields. The universe does not continuously pay an energy bill to keep electrons real. And in the next chapter, we can bring all of these pieces together and see how this strange quantum stability becomes the foundation beneath almost everything we call reality. After everything we have explored, we can finally return to the question that started this journey. An electron can remain inside an atom for billions of years. It can move through matter, interact with photons, participate in chemical reactions, travel through electrical circuits, and survive conditions ranging from the quiet interior of an ordinary atom to the extreme plasma of a star. Through all of this, it never seems to run out of the energy required to continue existing. So where does that energy come from? The answer is surprisingly simple. It does not come from anywhere, because the electron does not need a continuous supply of energy simply to exist. That may sound almost too easy after traveling through quantum mechanics, atomic orbitals, uncertainty, ground states, the exclusion principle, quantum fields, and the distant future of the universe. But all of those ideas were necessary because our original question contained a hidden assumption. We assumed that persistence requires power. And in fundamental physics, that is not generally true. Our intuition comes from a world filled with systems that continuously dissipate energy. Cars need fuel, computers need electricity, animals need food, fires need something to burn. A spinning object eventually slows because friction transfers its energy into the environment. Everywhere we look, continued activity seems to require a source. So when we imagine an electron endlessly moving around a nucleus, the obvious question is what keeps supplying the energy. But the electron was never a tiny machine. Inside an atom, it is not following the classical orbit that created the mystery in the first place. It occupies a quantum state. If that state is excited, the atom may transition to a lower energy configuration and release energy. Eventually, it can reach the ground state. And then there is no ordinary lower electronic state available. The electron does not somehow balance on the edge of collapse while constantly receiving energy from somewhere else. The ground state is already stable. Nothing needs to continuously hold it there. This is one of the most important conceptual changes introduced by quantum physics. Stability does not always need an active explanation. Sometimes the laws of nature simply provide stable states. Imagine asking what keeps a perfectly isolated object moving through empty space. If we inherited only everyday intuition, we might search for some invisible engine. But Newton taught us that the question is backwards. An object does not need a force to continue moving at constant velocity. A force is required to change that motion. Quantum mechanics gives us a strangely similar lesson about atomic stability. We do not necessarily need something continuously acting to preserve the electron's ground state. An interaction is needed to change it. If the atom is already in its lowest electronic state and remains sufficiently isolated, persistence is exactly what the laws predict. The absence of change does not consume energy. This distinction becomes clearer if we imagine waiting. Suppose we somehow isolate a hydrogen atom in its ground state. 1 second passes, then 1 minute, 1 year, 1,000,000 years. Nothing about the passage of time alone requires the electron to surrender a tiny amount of energy every moment. There is no universal tax charged for existing. If no allowed process transfers energy away, the state does not need to be replenished. This is why the age of the atom does not gradually drain it. The atom is not a battery, and neither is the electron. An electron can possess kinetic energy, but kinetic energy is not what keeps it alive. It can lose kinetic energy and still be an electron. An electron can participate in a bound state with a particular energy, but that energy is not fuel being burned to maintain its identity. Change the state and the energy can change. The particle remains. This is perhaps easiest to see with a free electron. Imagine an electron moving rapidly relative to you. It has substantial kinetic energy. Now imagine some interaction reduces its speed until the electron is at rest relative to your reference frame. Its kinetic energy in that frame has reached zero. Does the electron disappear? Of course not. It remains an electron. So whatever allows the electron to exist cannot simply be the kinetic energy we imagined it consuming. The same mistake appears in the atom when we picture orbital motion as something that must be powered. Once the classical orbit disappears, the need for a power source disappears with it. But quantum mechanics gives us more than a correction. It gives us an explanation for why stable atoms are possible. The electron cannot simply be squeezed into an arbitrarily tiny region around the nucleus without affecting its momentum distribution and kinetic energy contribution. The uncertainty principle changes the energetic cost of confinement, the electrostatic attraction toward the nucleus, and the quantum cost of localization combine to produce a lowest energy state with a finite size. Then, when many electrons are present, the Pauli exclusion principle prevents them from all occupying exactly the same state. Electronic structure develops. Shells appear. Chemical behavior emerges. The periodic table becomes possible. So the very quantum rules that initially seem bizarre are precisely the rules that allow ordinary matter to exist. If electrons behaved according to the simple planetary picture, atoms would be unstable. If electrons could all collapse without restriction into identical states, matter would have radically different properties. If atomic energies had no lower bound, stable structures would be impossible. The weirdness is not an inconvenience added to an otherwise ordinary universe. The weirdness is what makes the ordinary universe possible. Every solid object around you is evidence of this. Every molecule in your body depends on stable electronic structure. Every chemical bond depends on quantum mechanics. Every material used to build a city, computer, telescope, or spacecraft exists because electrons obey rules that seem deeply unfamiliar when translated into everyday language. And beneath even those atomic rules lies quantum field theory. The electron itself is not currently understood as a tiny mechanical object containing smaller pieces that must continuously operate. In the standard model, it is elementary. What we call an electron is an excitation of the electron field. Its existence does not resemble the operation of a machine. There's no known internal engine, no known fuel reservoir, no known components gradually wearing down. This helps explain one of the electron's most extraordinary properties. Every electron is fundamentally identical, not almost identical, not manufactured within some tolerance, identical in its intrinsic properties as far as we can measure. The same electric charge, the same rest mass, the same spin. An electron does not become a slightly different kind of electron after a billion years, and there is no known aging mechanism that gradually modifies those properties. This does not mean electrons cannot change state. They can. It does not mean electrons cannot be destroyed. An electron can annihilate with a positron under appropriate conditions. But that is an interaction. It is not exhaustion. The electron does not gradually become less real until there is nothing left. It either remains an electron or participates in a process that transforms the physical state into something else while the relevant conservation laws are respected. This difference between transformation and exhaustion reaches far beyond electrons. The universe is filled with processes in which structures disappear without fundamental physics, losing anything from its bookkeeping. A photon is absorbed. Its energy goes into another system. A molecule breaks apart. Its atoms remain. A star dies. Its matter and energy are redistributed. A living organism ceases functioning. Its particles continue participating in other physical processes. Nature is constantly rearranging itself. Energy changes form. Particles interact. Structures emerge and dissolve. But nothing in this picture requires energy to be consumed simply to keep reality existing from one moment to the next. Energy is conserved through the transformations. And this is where the original question becomes almost philosophical. Why did it feel so obvious that the electron needed energy to continue? Because we are temporary structures. Our own persistence does require a continuous flow of usable energy. You need energy to maintain the complex organization of your body. Your cells are constantly performing chemical work. Your nervous system maintains electrical gradients. Your body regulates itself against an environment that would otherwise push it toward equilibrium. For us, continuing to function really does require fuel. And because every machine we build works similarly, we naturally project this requirement downward onto the particles from which we are made. But the electron is not alive. It is not a machine. It does not need to preserve an enormously complicated internal arrangement. The electron is one of the ingredients from which systems requiring energy are constructed. We require fuel because of what electrons and other particles are doing collectively inside us. The electrons themselves do not require fuel for their existence. There is something strangely beautiful about this reversal. The temporary depends on the persistent. Your thoughts last seconds. Cells may survive for days, years, or decades depending on their type. A human lifetime lasts perhaps around a century. Civilizations exist for longer periods. Stars can survive for billions or even trillions of years depending on their mass. Yet the fundamental electron may outlast all of these structures. The arrangement disappears. The ingredient remains. An electron in your body right now may have existed long before you did. The atoms around it may have belonged to other molecules, other environments, perhaps other living systems or ancient geological material. Some of the matter making up Earth was forged through earlier generations of stars. The history of the material world stretches far beyond any individual structure. And yet the electron itself does not carry a visible record of that journey. It does not know where it has been. It does not arrive inside an atom exhausted from cosmic history. It simply obeys the same quantum rules it always has. This is why the question, how much longer can it keep going, has no known countdown attached to it. Within our current understanding, the electron is stable. Time alone does not appear to destroy it. If the distant universe becomes cold and dark, the disappearance of usable free energy would not mean that electrons had finally run out of energy. It would mean that the large-scale arrangements of energy had approached conditions where fewer useful gradients remained. Those are very different ideas. A universe can become incapable of supporting stars and complex processes while still containing energy. It can become incapable of supporting life while still containing particles. The end of activity is not necessarily the end of existence. And perhaps this is the deepest lesson the electron gives us. Energy is not simply the fuel of reality. It is a conserved property woven into the relationships, states, motion, masses, and fields that make up physical systems. Sometimes it is transferred. Sometimes it is stored. Sometimes differences in energy drive dramatic transformations. But an electron does not have to continuously spend energy to earn another moment of existence. A ground state atom does not need to fight against collapse. Stable matter does not need an invisible battery hidden beneath reality. The stability comes from the structure of the laws themselves. And so the answer we were looking for was hidden inside the question. Why does an electron never run out of energy? Because an electron was never running on energy in the way we imagined. It can gain energy. It can lose energy. It can transfer energy. It can occupy different states. It can participate in processes spanning everything from chemistry to starlight. But none of those energies are a fuel supply required to keep the electron alive. The electron does not keep going because something powers it. It keeps going because, unless an interaction changes or destroys it, continuing to exist is simply what a stable electron does. And after traveling through the atom, the uncertainty principle, quantum states, the exclusion principle, quantum fields, thermodynamics, and the possible future of the universe, we arrive at a remarkably quiet conclusion. The electron never needed to be kept alive. It never needed to be recharged. It never needed an engine. The mystery existed because we imagined one. And with that final piece in place, we can leave the electron where quantum mechanics tells us it belongs, not racing endlessly around the nucleus, not burning an invisible fuel, but existing as part of a stable quantum reality that has quietly supported matter for billions of years. So perhaps the mystery was never really about where the electron gets its energy. It was about the way we imagined the electron in the first place. We pictured a tiny particle racing endlessly around an atomic nucleus, moving for billions of years without slowing down, and naturally wondered what could possibly keep it going. Everything familiar to us eventually runs out. Batteries become empty. Machines stop when their fuel is gone. Living things require a constant supply of energy simply to remain alive. But the electron belongs to a very different world. It does not orbit the nucleus like a planet around a star. It occupies quantum states. Those states have specific energies, and eventually an atom can reach its ground state, the lowest electronic state available. There is nowhere lower to fall. Nothing needs to continuously push the electron away from the nucleus. Nothing needs to secretly replace energy that is being lost, because in a stable state, that energy is not continuously being lost at all. The electron can gain energy. It can lose energy. It can absorb and emit energy through interactions. It can move between atoms, travel through electrical circuits, participate in chemical reactions, and exist inside environments as extreme as the interior of a star. But none of that energy is fuel for the electron itself. An electron does not need to burn something in order to remain an electron. And perhaps that is the most important distinction we discovered. Energy is not simply the fuel of existence. For the complicated structures of our everyday world, energy flow is essential. A living organism must constantly maintain itself. A machine requires power to operate. A star can shine only while physical processes continue releasing usable energy. But fundamental particles are not machines. The electron has no known internal engine, no fuel tank, no mechanism slowly wearing away with age. As far as modern physics can tell, an electron that has existed for billions of years is fundamentally identical to one produced today. The universe around it can change completely. Stars can form and die. Planets can appear. Molecules can assemble into living systems and eventually break apart again. Entire structures can emerge from matter and disappear back into it. And through those transformations, electrons can remain. Not because something keeps recharging them, but because persistence itself does not necessarily cost energy. Sometimes a physical state simply remains until something interacts with it and causes it to change. And that may be the quietest lesson hidden inside the atom. At the deepest levels of reality, nature does not always behave like the machines we build from it. The rules underneath our world are stranger, simpler, and in some ways far more stable. Quantum mechanics prevents the atom from collapsing. Ground states give energy a lower boundary. The exclusion principle helps create the structure of matter. Quantum fields give us a deeper description of what particles actually are. And from those strange principles comes almost everything familiar to us. Every object around you, every molecule in your body, every electrical signal passing through the device playing this video, even the thoughts you're having while listening. All of them depend, somewhere underneath, on electrons quietly obeying rules that seem completely unlike our everyday experience. So the next time you see the familiar picture of an electron circling an atomic nucleus, remember that reality is far stranger. There is no tiny planet endlessly burning through some invisible supply of energy. There is a quantum state, a stable structure, and beneath it, a universe whose fundamental ingredients do not need fuel simply to continue existing. If you enjoyed this journey, subscribe to Science Sleep Theory for more calm explorations into the deepest questions hidden beneath ordinary reality. And if you're listening as you fall asleep, you can leave the electron exactly where we found it. Not racing, not struggling, not slowly becoming exhausted, simply existing within the quiet structure of quantum mechanics. The atom remains stable. The electron remains an electron. And the universe continues building almost everything we know from particles that never needed to be powered in the first place. Thank you for spending this time with Science Sleep Theory. Sleep well, and keep wondering.